Okay, good afternoon, everyone. So, yeah, we have a series of talks this afternoon around mathematics of AI. And we're going to start with Clément, who is your postdoc, right? At ENSAE, at Institut Polytechnique de Paris. And Clément will talk about mirror and preconditioned gradient descent in Wasserstein space. The floor is yours.
Thank you for the introduction. So I'm going to present a joint work with Théo Isida, Adam David, Pierre Seilobin Frankowski, and Anna Corba, in which our goal is to generalize the mirror descent and the preconditioned gradient descent algorithms to the Wasserstein space. So in this work, we aim at minimizing some functional f with respect to a probability distribution. So this is an important application in machine learning, which can be interesting for many applications. So, for example, when we are interested into sampling distribution from which we know only the density up to a normalizing constant, one way to solve this problem is to minimize the Kullback-Leibler divergence, which can be written as the potential energy plus negative entropy term. And in that case, it does not depend on the normalization constant, which is unknown. So this is a good functional to minimize in order to be able to provide new samples from this distribution nu. Another typical application is generative modeling, where instead of having access to the density, we have access to samples from mu. In that case, what we can do to solve this problem is to minimize some distance or divergence between the measure mu and the measure nu. And for the distance, we want to be able to evaluate it with respect to samples. This problem also appears when we want to minimize neural networks by seeing the weights of the neural network as samples of a probability distribution. So this was done, for example, in a paper from Glenek Shiza and Francis Bach. And this provides a way to analyze the optimization of neural networks. And finally, also another example of applications that we'll also talk later is the modelization of dynamics of population of cells. So first, we'll start with a quick detour by an optimization on Euclidean spaces. So here we want to minimize some functional f from RD to R, which is typically convex. And one way to solve this problem is to try to find its gradient flow, so to follow this gradient flow, which is a curve which minimizes the functional by following the steepest descent direction. So when the function f is differentiable, this is a solution of the following ordinary differential equation. But usually, we don't know the solution of this problem, so we need to discretize the ordinary differential equation. And when we do, for example, a forward alert scheme, we recover the well-known algorithm, which is the gradient descent, and which can be seen as an approximation of the gradient flow, so as a discretization. Something interesting about the gradient descent that we'll use later is that it has also a variational form, which is like this. So basically, it can be seen as the solution of the problem of the minimization of the square Euclidean distance plus a linearization of f around sk. So this algorithm is well known, so for which it has been a lot studied theoretically, and we have a good idea of on which conditions we need for it to converge. So typically, a set of sufficient conditions for it to converge is to require f to be beta smooth and alpha strongly convex. So just as a reminder, f beta smooth means that we have the following inequality. And in that case, if f is beta smooth, we know that the function f is non-increasing along the scheme, so which is given by the descent lemma here, because this is greater or equal than 0. And if we ask also f to be strongly convex, alpha strongly convex, we can show that it converges actually to the minimum. Okay, so now the question is what happens when f is not beta smooth? In that case, we don't have any guarantee for the optimization of the function f. And one solution to solve this problem is to try to change the geometry. And one way to do it is to use, for instance, the Bregman divergence that I will introduce now. So this is defined, we take f, some strictly convex function, and then the Bregman divergence is defined as phi of x minus the Taylor expansion around y. So this is well a divergence because since phi is strictly convex, this is greater or equal than 0 by definition, and this is equal to 0 if and only if x equal to y. And then, to do optimization in the space endowed with this divergence, we just plug it into the variational form in place of the squared Euclidean distance, and we obtain what we call the mirror descent algorithm. So first, we also have a variational form, but we also can also compute this minimization problem in closed form by taking the first order condition, which gives the following algorithm, which is what we call in general the mirror descent. So basically, this algorithm takes a sample xk to a kind of space of gradient or dual space by using the gradient of phi. And then in this second space, we do the gradient step. And then we go back to the original space by using the inverse of the gradient of phi, which is the gradient of phi star, where phi star is the Legendre transform of phi. As a remark, the mirror descent can be seen as a strict generalization of the gradient descent, because if we take phi as the squared norm, we recover exactly the gradient descent, because the gradient of phi is identity in that case. So this algorithm has also been well studied. In particular, the convergence conditions can be obtained by similar conditions of gradient descent. So instead of requiring f to be beta smooth, we will ask f to be beta smooth relative to phi, which means that the Bregman divergence of f is lower or equal than the Bregman divergence on phi. In that case, we also have the descent lemma. And if we also ask f to be alpha convex relative to phi, which means that we have the opposite inequality between the Bregman divergences, but which is also equivalent with f minus alpha phi to be convex, in that case, we also can show that it converges with the same rate towards the minimum. And also notice that if we take phi as the squared distance, we recover exactly the same conditions of convergence as for the gradient descent. So a second algorithm we'll be interested in is the preconditioned gradient descent, which was proposed and studied by Madison et al. In 2021. So here we want to minimize the function g now, and we take h some strictly convex function, and the preconditioned gradient descent corresponds simply to the gradient descent, where we use some kind of preconditioner on the gradient, which is the same obtained as the gradient of the Legendre transform of h. And it has also a variational form, which is of this form. So basically, here the cost is a translation invariant cost, and which we use instead of the Bregman divergence. In that case, if we take also h as the squared norm, we also recover gradient descent. Interestingly, this algorithm is very related to mirror descent, and this can be observed because if we do a relabeling, for example, we take g equal to phi star, x star equal to f, and y equal to gradient of phi of x, then just rewriting the equation, we recover exactly the mirror descent algorithm, but where we have swapped the roles of the minimizer and of the preconditioner. And this is also what we recover when we do the analysis of the convergence. So it has been shown by Madison et al. That it converges if now h star is smooth relative to g star and is also alpha convex relative to g star. So we see that we swapped the conditions for the beta smoothness and alpha convexity. Also, the descent lemma is given now on the gradient, so it also allows to measure that we converge towards the minimum, because common the gradient is equal to 0, this is the minimum, but this is not the same measures of convergence. So just to summarize the two algorithms, the mirror descent, we project the samples into the dual space, then do the gradient step and go back to the original space. When for the precondition gradient descent, we project the gradient back to the space of samples and then do the gradient step. Okay. So now, in this work, we are interested in doing optimization over probability measure. So we need to undo this space with some kind of structure. And in the following, we'll use the structure of the Wasserstein space, so which means that we will undo the space of probability distribution with what we call the Wasserstein distance, which is defined as the infimum over the set of couplings of the integral of the squared norm. But this is not really important here. What is important is that when we undo the space probability measure with this distance, it allows us to define, to have, so this space has a Riemannian structure, and in particular we can define a lot of notions that we know from differential geometry, namely geodesics, tangent space, and in particular what we are really interested in as we want to do optimization, we can define a notion of Wasserstein gradient, which I will not really introduce rigorously here. I will just say that the Wasserstein gradient is a map in L2 of nu, so from RD to RD, which have some order moments, and it satisfies some kind of Taylor expansion, or in particular, the Taylor expansion, when we perturb mu with some map T in L2, we have the following so Taylor expansion. Examples of Wasserstein differentiable functionals are, for example, the potential energy, which is linear in mu. In that case, the Wasserstein gradient is simply the gradient of V, which does not depend on mu. And another more interesting example is the interaction energy, which is quadratic in mu. And in that case, we see that the Wasserstein gradient is obtained as the convolution between the gradient of the potential W on mu. So here we see that there is a dependence in mu. So now that we have a notion of gradient, we can do optimization. And one way to do it is to use the Wasserstein gradient descent algorithm, which is defined like this. So we use first a variational formulation, which is very similar with the one of gradient descent, but now we use with maps on L2 of mu, and with the linearization obtained with the Wasserstein gradient. So this gives what we call the Wasserstein gradient descent, and we can find a closed form for this expression by taking the first order conditions. In that case, the update Tk plus 1 is just identity minus 2 times the gradient, so this is exactly gradient descent, just with the Wasserstein gradient which depends on mu k. And then, since we want to move the distributions, we take what we call the push forward of mu k with this map. In general, we can't work directly with mu k in practice because we don't know it. So what we really do in practice is to sample at time 0 some particles. Then at each iteration, we first approximate the map Tk plus 1 by approximating the gradient with the current mu k, which is just a discrete distribution. And then we apply this map at each point, and we move each particle. So our contributions in this work are to study the scheme, which is obtained by plugging, instead of the L2 distance, other type of divergences into the variational form, and to study how to compute it in practice and to provide convergence conditions. So to be more precise, we used first Bregman divergence on L2 of mu, which allows to extend the mirror descent algorithm to the space of probability distributions. And then we use some kind of translation invariant cost, which will allow to extend the preconditioned gradient descent. Okay. So now I will introduce the mirror descent algorithm on the space of probability distribution. So first, we need to define the Bregman divergence on L2 of mu. Fortunately, it is defined similarly as on RD, just using the right notion of derivatives on this space. Some things we can observe is that we also recover the same result. So if we take a squared norm, we recover the square distance. So it will be just a generalization of the regular L2 norm. And here we need also to choose a class of function for the Bregman potential phi. And here we will mostly focus on what we call push-forward compatible map. So it means that we have a map phi which is defined on the space of probability distributions, and we lift it on the tangent space, which defines phi mu here as phi of t push 1 mu, which is a map on L2 of mu. And we can also relate the notion of differentiability. So we know that if phi is Wasserstein differentiable, then phi mu is Fréchet differentiable, and we have a relation between the gradients. So since we want also to analyze the convergence of this algorithm, we also need notion of relative smoothness and convexity on this space. So first we can define on L2 of mu the notion of beta smoothness and alpha convexity by using the same definition as on RD, so with the right inequalities in the right sense between the Bregman divergences. And then to define notion of relative smoothness and convexity on the space of probability distributions, what we'll do, we'll take a curve mu t, which is obtained by taking the push forward of a linear interpolation between two maps, S and T, and we take the push forward on mu. So it defines the curve on P2, so on the space of probability distributions. And then we will say that F is beta smooth or alpha convex relative to G along this curve if the inequalities between the Riemann divergences are satisfied for the functions lifted on L2 of mu with the push forward. So we go on the tangent space and verify that our functions are convex in the tangent space along this curve. So now we can finally introduce the mirror descent on this space. So we just plug the Riemann divergence into the variable form, and the first question we ask is, can we compute it in practice? And the answer is not always. So first, if you take the first order condition, we obtain the following equality, which is exactly the same as we have on RD. And now the question is, can we invert in practice this guy, so gradient of 5 of mu k? And if we can, we would have directly a closed form expression to compute the scheme. So if we take phi as a potential energy, here, now the gradient would just be the gradient of V composed of Tk plus 1. In that case, provided that the gradient of V is invertible, we have a closed form for Tk plus 1, which is exactly the same as the mirror descent, just with the Wasserstein gradient. So this is kind of what we would expect. But if we take phi, which would be more general, so any other push-forward compatible functional, for example, then in that case, the gradient is implicit in Tk plus 1, and we can't, so it is not easy to invert it directly. So in general, what we need to do is to use some root solver algorithm to compute it. So now, for the theoretical analysis of this scheme, first we observe that so to have the descent property, we need to assume that F is beta smooth relative to phi along a curve which is simply the curve of iterates. So under the same condition as on Euclidean spaces, we have the descent property. Then for the convergence, it is slightly more complicated. We first need the beta smoothness and alpha convexity relative to phi along the right curves, which is the same as on RD, but we also need a third assumption, which is this one, which is an inequality between Riemann divergences in the space L2 of mu k and L2 of mu k plus 1. So we need these assumptions because at each step we do the optimization in a different space L2 of mu k. So that's why we need these technical assumptions. Provided we have these three assumptions, we can show the same convergence rate as on a Euclidean space. So now the question is, can we verify that this third assumption is well verified for some phi? And we answer this question positively by defining an optimal transport problem which is associated to the Riemann divergence, like this, and by observing that it is always lower or equal than the Riemann divergence between two maps here, provided that they give a coupling between the right measures. And then we deduced that this inequality would be true, provided that this problem admits an optimal transport map. So we provided conditions to obtain an optimal transport map for this problem. And by leveraging simply Brownies theorem, we deduce that if mu is absolutely continuous with respect to the Blum measure and the gradient of 5 mu is invertible, in that case, we have an optimal transport map and the inequality is satisfied. So this is, for instance, the case for a potential energy with a gradient of V which would be invertible, so if V is strictly convex, for instance. So then we also studied the preconditioned gradient descent, which is defined likewise by using a translation invariant cost here. So in that case, we also have a closed form, which is the same closed form as on RD, so with the Wasserstein gradient. So for now, it is expected, and then we also showed that we have the same convergence rates as on RD, using the right notion of relative smoothness and convexity of phi of h star relative to some kind of Legendre transform of f along the right curves. So now I'm going to talk a bit about applications, but first, we saw that to have the convergence guarantees for the scheme we studied, we always need to have relative smoothness and relative convexity between the functionals, but I did not tell how to verify this in practice. So in general, what we would do is to look at the Wasserstein Hessians and try to compare them, but it is actually quite painful to work with Wasserstein Hessian. So we try to find pairs of maps of functionals for which it is easier to show the beta smoothness and alpha convexity. And we found it, for example, if we choose f and phi to be of the same class, so either potential energies or interaction energies, in these cases, we can lift the relative smoothness or convexity between the potentials on RD to the functionals on the space of probability distribution. So in that case, it is easier to show. Also, if we take a functional which is a sum of two convex functionals, then we can show easily that f will be one convex relative to both of the functions. So now, in terms of applications, first we wanted to verify that we can actually use other potentials than just the potential energies, other Bringman potentials than potential energies. So, and we tried with interaction energy. So here, we want to minimize an interaction energy with this kernel. So this is a problem which is not convex, so we don't expect it to converge to the minimum. And then we tried to use as Bringman potential also an interaction energy, but for which the W will be smooth relative to K. So in that case, we expect to have at least the descent lemma which is verified. And we tried several kernels, and we showed, so we see empirically that the values of the functional is well non-increasing along the schemes for these four kernels, so it means that the descent lemma is verified. Moreover, if we choose it wisely, we see that it converges towards a pretty good minimum, which is this ellipsoid. As a second application, we wanted to, so we studied the case where we want to minimize the Kullback-Leibler divergence and where the target is a Gaussian. So this is an interesting situation because in that case, in general, we have access to, we know that at each step, the measures will be Gaussian for when we do the Wasserstein gradient descent, and we can compute everything in close form, so we can really see what happens in practice during the optimization. So what we would usually do to solve this problem is to do a forward-backward optimization scheme, because so here normally what we do would be a forward step on the smooth part, which is the potential energy, and then a backward step on the non-smooth part, which is the entropy. And in that case, we can show theoretically that it converges, but in practice, it is actually pretty slow as long as the optimal covariance sigma is not the identity. So we try to accelerate this optimization scheme. And the first proposition is, so first solution is to use a preconditioned forward backward. So we still do a forward backward scheme, but with a Bringman divergence, which is for which the Bringman potential is chosen as the actual optimal potential energy. So in that case, if we do the schemes, we see in red here that it converges very well, but we can say that it is kind of changing because we use the information of the optimal potential that you should actually not know. So then we try the third solution, so the second solution, which is to use as Bringman potential the negative entropy. So this is interesting because the entropy was the non-smooth part because of which we needed to do the forward-backward scheme, but now the entropy is smooth relative to itself, and it is easier to show that the potential is smooth relative to the entropy. So in that case, we can use directly the mirror descent algorithm. And then we also need to do some kind of restriction to Gaussians to make sure that we have closed form at each step. So this is a kind of projection. And we obtain a closed form at each direction for sigma. And in that case, by plotting the values of the KL divergence along the scheme, we see that it converges so very fast without taking into account the information of the optimal potential. Then, as the final experiment, we wanted to verify that choosing a choosing the right preconditioner can be interesting. So here, this is a kind of toy setting where we have cells. So we have a untreated cell mu0, and then we apply some drug to the cells, and we remeasure it, and we obtain the cells at another time, which are perturbed. And then our synthetic task is to minimize the divergence between mu and nu, to move mu0 towards nu. And as the preconditioner, we propose to use the polynomial preconditioner of this form, which can be interesting for functions which grow like this on the minimum. So of course, in practice, we can't verify it. So we just try several A and measure and compare the solutions. And we optimize the 3 different divergences, so the slice Wasserstein distance, the sinker divergence, and the energy distance. And here on this plot, what we did is plotting the values obtained without preconditioning and with preconditioning. So it means that if the points are below the line y equal x, it means that we obtain either a better minimum with the preconditioner, or we converge towards in less iteration. And we see that there are a lot of points below the line, so it seems to work pretty well. So as a conclusion, in this work, we propose a way to extend the mirror descent and the preconditioned gradient descent algorithm on the space of probability distributions. We also provided a convergence analysis for both these schemes, and we also in the paper, we analyzed the forward-backward scheme. And as some perspective, it would be interesting to try to find more examples of pairs which satisfy the relative smoothness and relative convexity condition, because we saw that it was pretty hard to find actual interesting examples which satisfy both these conditions. And so it would be interesting to analyze the Gaussian mirror descent scheme, which works pretty well, but which does not fit the theory we did. So thank you for your attention.
Thank you, Clément. Any question for Clément? Yeah, question there.
Thank you for your presentation. I was wondering how much more computationally expensive are the methods that you're presenting today compared to other optimizing schemes?
So you mean like this one, for example?
For example, this one, yeah, exactly.
So
because you said it converges faster, but like it's just in terms of number of iteration of the algorithm, but not in terms of how much time it takes to compute every iteration, right?
Yeah, so I think it is, so using the preconditioner here, I think it is negligible in time, so it should not do, it does not induce a big computational overhead to use the preconditioner, compared to using just the Wasserstein gradient descent.
And compared to just using standard PGD or anything like a gradient descent or anything like this?
So so here we want to minimize over distribution, so we can't really apply directly gradient descent.
Okay, so it's specifically targeted to problems where you cannot use. Okay, yeah. Thank you for the precision.
Now we have a question here.
Yeah. So it's, I'm just trying to wrap my head a bit around certain things because I got a bit lost. If I understood correctly, Wasserstein gradient descent, you show that it is sort of can be viewed as a generalization of mirror descent. Correct?
So can you repeat, please?
I said, you're showing that Wasserstein gradient descent can be seen as a certain generalization of mirror descent. Okay, now my question is, if we take the step size in mirror descent and we take it to 0, we obtain a flow which is like a Hessian-Riemannian gradient flow. Yeah. All right, great. Now, if we take the corresponding step size of Wasserstein gradient descent to 0, would we be getting the same flow, or will we be getting a completely different flow? I'm just trying to understand the distance, so to speak, of the two algorithms.
So, yeah, when we do Wasserstein gradient descent, what we approximate is what we call the Wasserstein gradient flow that I did not introduce here, but instead of an ordinary differential equation, we have what we call a continuity equation, which is a partial differential equation. So it is like the derivative of mu t plus divergence of mu t times the gradient of the functional. And if we do the mirror so the mirror descent that I introduced here, we would have also a term of Hessian into the divergence, but which would be the inverse of the Wasserstein Hessian.
I understand, but then a follow-up question. Since you have this link, doesn't this mean that you can directly view Wasserstein gradient descent like a retraction Riemannian method of the Wasserstein flow and analyze it like a standard Riemannian retraction method?
So yeah, the Wasserstein gradient descent can be seen also directly as a retraction, so as a Riemannian gradient descent. Yeah.
Okay.
Using the right notion of exponential map, which is exactly, so for the gradient descent, it's exactly identity minus 2 times the gradients push forward mu k, so this would be the exponential map.
And the analysis differ? I mean, do the two analyses diverge? Do you get different results? This is what I wanted to get at.
No, I think we get similar results. Yeah.
Okay, okay, perfect, thank you.
Any other question? Yeah, maybe a last question from my side. What happens if you consider, entropic regularized optimal transport, if you regularize, the map?
So for the functional to optimize or for the geometry?
I think it looks like what you have
So,
there. Yeah, or something like sinkhole divergence. No.
Yeah, but so here there are two things. Either we can consider, for example, the sinkhole divergence as the objective to minimize. So this is, for example, one of the examples here.
Yeah.
Here, this is the sinkhole divergence. And I don't know if it is the question.
Yeah.
So yeah, so we can compute this Wasserstein gradient and use it in our scheme. Yeah.
I didn't see in your convergence results the dependence on the dimension. I missed it. So how this depends on the dimension of the problem, on D?
I don't know.
Honest question. No?
Yeah.
Vas-y, Sam.
Okay, sorry. The rates depend on the smoothness and convexity constants, so this might be hidden there.
Okay. Thanks a lot, Clément. Thanks again.
Et voilà, parlez là aussi.
Ah, pardon, merci.
Comme vous voulez.
Je n'ai pas compris. Ah, soit là, soit là. Okay. Thank you. Okay, so yeah, I'm going to talk about DU-Shapley. This is a really nice slide. I had much trouble to fit my title in the template, and it was already done by somebody else. So, anyways, okay, that's mine. Not as good. Okay, so I'm at Inria, and I'm part of a team called FAIRPLAY. So I'll just spend one slide here. Sorry. To discuss quickly general contribution of FAIRPLAY in the Foundry PEPR project. So this is FAIRPLAY is a joint team between the Criteria AI Lab, ENSAE, and Inria in Saclay. And there's a number of permanent and non-permanent researchers involved, so myself, Vianney Perchet, and some PhDs and postdocs. And the work that I'll present today is done in part with some of these other members of the team. And besides what I'll present today, we work on multiple different topics related to the project, on fairness and privacy in particular. And usually things that are in between learning and game theory. And what I'll present today is a very simple problem on data valuation. Okay? So the idea is the following. If you want to do machine learning, usually it happens that multiple different entities possess different data sets. And you may want to learn a single model for which all these data sets could be useful, right? So here I have several players. I'm not sure if I can use... no, right? It works? This is, yeah, okay. Okay. Okay, so here you have 3 players or a certain number of players. All of them have data sets that could contribute to learning a model. And what we want to do is try to quantify the contribution of each of these different data sets to solving some machine learning tasks. So that could be, for me, that's going to be regression because it's a simple model here, but that could be something else. And that can be useful in multiple different applications. So I mentioned here 2 of them. Mechanism design is if you'd like to incentivize people to share their data, you need to understand how much they contribute when they give data. Is it useful or not? And try to reward according to that estimation. That can be useful also in federated learning. And one way to do this, which is the way that I'm going to present today, is to use cooperative game theory, where we model this problem as a cooperative game, and we try to compute the Shapley value. So, if I just in a few words, Shapley value is a very standard solution concept for cooperative games. It has found its way in machine learning in many different places, and in particular in data valuation, where you try to value to estimate the value of a data point in feature selections or interpretability and things like this. Here you might want to estimate the contribution of a feature. So maybe the ones with the most contributions give more explainability or something like this. What we want to do here is estimate the contribution of a whole data set. And what's going to be the main issue is actually very standard in Shapley value. In using Shapley value is that you can write what the Shapley value is. It's very easy. Well, it's sort of easy, and but computing it is very difficult because it's computationally difficult. Okay, so let me go a bit into the model. So we have a regression model. We have I players. So this set here is a number of players, or I call them players or agents indifferently. And each of them has one data set, which is called DI here. And this is data set. It has features X. This is fairly standard. Features X and a label Y. And this data set comes from a distribution Fi here. Okay? And what's going to be most important for us is how large is the data set. And so we denote this by Ni. This is the number of data points in the data set. Okay, that's we're going to say that in many cases we can reduce the contribution of a player to the number of data points in their own data set. Okay, and so we assume this is a regression model. We assume that the label yi is a function f, which is a function of the features plus some noise. Okay, and the noise is a Gaussian noise. This is a normal distribution with some variance, and the function f is the unknown thing that we are trying to learn. Okay, and so we want to estimate this function, and we want to estimate it as the minimum of the risk, which is the expectation of g of x minus y squared. So we take a squared loss here, standard risk, and we try to minimize this. Okay? So there are multiple different ways of doing that. One way is, so this is just regression here. One way is if it's a linear regression, then you can have a parameter, and I'll discuss that towards the end. There's another way, which is a very well-known way, which is called the binning method. And what is the regressogram? And what this is doing is we're trying to do this in a non-parametric way. Just to be a bit more general, we don't want to impose linear regression up front. So we do this in a non-parametric way. So this is the data. This is a function f that we're trying to learn. And the way we are going to do that is we fix some bins. Okay, so bins on the x-axis here, we have capital B is the number number of bins, and so what we're going to do is try to approximate this function f by a function which is constant in each of these bins. So this red function here is something that's constant in each of the bins, okay? And if we do this, then you can rewrite the risk as this is the initial risk, this is the difference between f hat, this is the estimate, and the actual function we try to estimate. This can be decomposed into the estimation error, which is the difference between the estimate and the approximate function plus approximation error here. And what's interesting for us is to understand how much data points are going to contribute to the estimation. So in fact, we don't care very much about this. We can control this by the binning, and there are some standard metrics methods to do this. You need to choose the number of bins in a smart way so that this is not too large. But what we're going to really care about is this part here. Okay, so I said differently, we have here this, it's really too hard to read backwards, so I will do it like this. You see the, okay, I will do that. Okay, so this is my risk, and then I have the estimation error, the approximation error. The estimation, again, this approximation error, I can make it decrease properly by choosing the number of bins, and I'm going to care here about the estimation error, okay? And so if I restate my initial problem, the data set valuation problem is quantify the contribution of the player when they share the data set towards decreasing the estimation error, meaning that I'm going to only care about this term from now on, okay? And this will, of course, depend on whether or not players share the data. Okay, so now we're going to model this as a cooperative game. So a cooperative game is two things. It's a set of players. So my set of players has not changed. It's still the same set of players. All the players who own a data set and may potentially be sharing it. And the value function, this is the second thing that defines a cooperative game. And the value function is a function from any subset of player to R. So it assigns a value to any subset of players. And the value for us is going to be the opposite of the, whoa. Okay, so, okay. Here it's going to be the opposite of the estimation error, okay? So now this formula is maybe a bit, okay, maybe I will try again this. So this formula is a bit too generic for us to do something, but with the models that we had from before, this regressogram, this, you see, the contribution of each player can be divided into the contribution of each player to the estimation of the constant value function inside each bin. So we can divide this value function here as a sum on all the bins of the estimation error inside the bins. Of course, weighted by the amount of points, the prevalence of the bin, but essentially this is the sum inside the bin of something that is only, the sum, sorry, on all the bins of something that happens only inside the bin, okay? So from now on, what we can do when we have this is we can just look at every bin individually, and then at the end of it, we're going to sum everything. You'll see that this works out because Shapley value is additive, and so it's okay to divide it into a sum of different values, and for us, the different values are going to be the values in every bin, okay? Okay, so we are going to measure the agent's contribution in each bin, and then for each bin we have this term here to look at. And what's interesting is because inside the bin we have a function which is constant, we're trying to estimate just a constant value, then it doesn't matter where the points are. If the bins are small enough, it only matters how many points you have in the bin. So once you have done bins small enough such that the constant value function is a good enough approximation inside the bins, you can only start looking at the number of points inside the bin and forget about the rest. And this is going to be very interesting, important for us, because now this value function, which is a function of a set, which is a complicated set of data points, now becomes a function, a much simpler function. Sorry, not another function, which I now call W, of a much simpler quantity, NSB, which is just a number of points. So it's a scalar quantity. It becomes a function of a scalar quantity. It's just a number of points inside the bin. Okay, and this is just to note that from linear regression, you have formulas for how this W function is. If you have a certain number N SB of bin here, you'll have that the value function has this form, minus D. D is the dimension here. Sigma epsilon, this is the squared variance, not squared, just the variance, divided by number of points minus D and D plus 1. And D again is the dimension here. Okay? Okay, so we have this thing that's become now a very simple function of a scalar quantity. We're going to try to compute the Shapley value. What is the Shapley value? It's a classical solution concept in cooperative game theory. It's the most used solution concept, I think, to some extent. And it's defined as the average marginal contribution of player I to all the sub-coalition, all the subset of players that does not include I itself. Okay? So the average marginal contribution, it means we're going to sum on all the subset S, which are subset of players not including I itself. And we're going to look at the marginal contribution, meaning a value of the coalition S with I minus value without I. Okay, so that's the marginal contribution here. Okay? The Shapley value can also be defined differently by some axioms. It's a unique semi-value that satisfies a number of axioms. There are 4 axioms, additivity, symmetry, dummy, and the fourth one, which I forgot. But this is also a complete definition. And the reason why it's well appreciated, let's say, in many problems is that it's sort of as a fair evaluation of the contribution. Why fair? Because, because it's there are 2 ways of seeing this. One is that it's an average marginal contribution, so you sort of consider how much you contribute on average to any possible sub-coalition. That's one way to see it. The other way is it satisfies the symmetry axiom, meaning that 2 players who contribute the same get the same Shapley value, and that's an interesting property at least. Okay, so that's very good. If you rewrite this very slightly, you'll see that now, let me maybe just skip ahead a little bit. Here, I just make the sum on the bits because for me, I have, what I care about is looking independently at what I have inside the bins, and then this thing that I do here is I replace my function of a complicated subset by the function of a very simple scalar quantity here. Okay? And at the end, I have a sum on the bits of a, like, inside the bin Shapley value, and I want to compute that. There comes the standard problem in Shapley value is that it's intractable. By intractable, I don't mean theoretically, but computationally, it's not possible to compute that. The reason for this is there is a sum here on all the subsets, and there is an exponential number of subsets, and we cannot compute the average over an exponential number of subsets. So that's a standard problem with Shapley value. But because of the structure that we have here, we can propose a more efficient approximation for exactly this type of dataset valuation problems. Okay, so let me now discuss that. So this is we look at the Shapley value. So it's as if we take just one bin. Okay, you can think of it as a single bin. Okay, and the Shapley value. This is really just a rewriting. We can rewrite it as the expectation on first we draw a number k, which is a uniform number between 0 and I minus 1. This is going to be the number of players in the subset that we choose. And once we have fixed k, we choose the subset of size k. So it's exactly the same sum as before, but before choosing the subset, we fix its size. We fix uniformly the size of the subset, and then we choose the subset. Uniformly on all the possible subset of this particular size. Okay. Now, of course, if we want to estimate this is coming back to exactly the sum as before, which is an exponential number of terms. But what simplifies is that it turns out that if I look at this quantity, n of s, here, it has a simple distribution. Can you see what distribution it will have? So here, basically, I'm picking a number k, which is a number of players. Then I'm picking a subset with that many players. So let's say my total number is 10. I will pick a subset of 5 players. And now I randomly pick a subset of 5 players. And I look at the sum of number of points for each of these players. Okay? What is the distribution of this sum? Well, it turns out it's uniform, which is, by the way, the reason why it is called discrete uniform Shapley, because this distribution is uniform. So I'm not sure, I was making a test. I'm not sure if it's obvious. It was not obvious to us. We looked at this and we said, oh, it's uniform. And then we thought we are stupid to not have thought before that it should be uniform, of course. And I'm still not sure. But at least now I can for sure show that it's uniform. So here, what you can see is exactly in blue, it's the distribution of this quantity, NS, in blue, and the orange, or I'm not sure what color you see, brown or something, yellow, maybe pink, I don't know. But this is a uniform distribution, okay? And so what you should see is here, there are not too many players, so I is equal to 10. This is the total number of players from which I drew k. And that's 10, 50, and 500. And what you can see is the blue thing is becoming closer and closer to the brown thing here, which is uniform, okay? And so now we have this thing. So first of all, we can show this. So this is this is an asymptotic guarantee. So we can show this rigorously, that this quantity, the sum, the number of points in a subset S of size k divided by the total number of points in all the players except for I, this converges towards a uniform distribution between 0 and 1. And we can use this to come up with an approximation for the DU-Shapley, for the Shapley value, which we call DU-Shapley for a discrete uniform. And it's very easy. What we do is, because this number of points is uniform, we are just going to pick some uniformly distributed numbers and compute only on those. So this is exactly what we do this. Basically, we look at I different values, which are k mu to the minus I. And mu to the minus I here is just the total number of points, everything except for everyone, so every agent except for agent I. And essentially what we do is we have this maximum number of points for the subset, and we just take I different numbers here, exactly uniformly spread on this. And we make a sum of the marginal contribution of player I to a subset with exactly that number of data points. And it's possible because now the value only depends on the number of data points. Okay? So that's called the discrete uniform Shapley, and we can show that this is a non-asymptotic guarantee. So basically what we show here, this phi is the Shapley value. Psi here is the discrete uniform Shapley value, so this is the approximation. And so we can show that the difference between the two is less than this quantity, which I really cannot read backward. So which depends, so let's just look at what it depends on. The formula exactly doesn't matter, but basically this is 1 divided by some constant divided by I. I is the number of players, the total number of players. So this is going to decrease like 1 over I. Not exactly, because there's a small log of I here, but okay, this is still log I over I. Now it's controlled by this W infinity. This W infinity comes from this condition. The condition says that x squared times the second derivative of W. W is a valuation function. Should be bounded by this quantity W here, okay? And it's also controlled, if you look here, n minus I max. This is the largest number of points of any player except for I. And this tau minus I squared is here the ratio between this maximum number of points and minimum number of points. So this is sort of controlling the disparity of number of points between the different players within these I players. Okay. Okay, and so basically, besides this, so by the way, this there are two assumptions to this. The W must be twice differentiable, and the second derivative must be bounded by this quantity here, and those two are, for instance, valid for the linear regression with quadratic loss. Okay. Okay, so now if we look, if we try to compare this to existing methods to do approximation of Shapley value. So the only, the standard existing method is called Monte Carlo. So Monte Carlo is essentially you have the sum with exponentially many terms. Monte Carlo is in some way you just randomly draw some terms in this sum. It can be either you first draw the number of players and then you draw the number of the player with this number being fixed, or sometimes people draw a permutation and then they take the first k players in that permutation. Both work equally well. And in fact, when you do Monte Carlo, well, the more you draw, the better the approximation. So you have exponentially many terms. You're not going to draw exponentially many, but if you draw more, you have a better approximation. This is given by essentially this equation here, which tells you that if you want your approximation to be bounded by epsilon with probability at least 1 minus delta, you need a number of permutation drawn, T-perm, this is the number of permutation drawn here, which is growing like I times log of I divided by epsilon square. And so you need something that grows like 1 over epsilon square. This is for Monte Carlo. Whereas for DU-Shapley, you need I function valuation. Because we have something uniform with just I checkpoints linearly spread over the line. And so if we look at this looks like, this is the expected error as a function of the number of players. So on the x-axis, this is the number of players from 10 to 10 to the 5. And so what you see, so okay, this curve here is the Monte Carlo, the orange one is the Monte Carlo, and the blue one is our approximation. And what you can see is basically our approximation decreases with the number of players, which makes sense because it's asymptotically, it works when the number of players grows large, and the error decreases like 1 over the number of players. Whereas Monte Carlo is more or less constant, and here for comparisons, we draw a number of permutation equals to the number of players, so that sort of, at least morally, you can think of it as spending the same amount of computation for both methods, for both approximations. Okay, this is just another example where we just have two bins. There is a blue bin and a red bin, sorry. And here, this is also, wait, this is increasing. Ah, no, it's, okay, it's decreasing, of course. This is also the mean squared error, which is decreasing as with the share of utility function evaluations with respect to DU-Shapley. So basically here, our approximation is this one here. This is DU-Shapley, this is this line here, It's constant because it's normalized to exactly this line, okay? And that's how much you get with Monte Carlo if you increase the number of evaluations. And you see that if you have many players, well, you need really a huge number of evaluations in order to have an approximation equal to the quality of errors. Okay, so that's basically what I wanted to say. I have literally no idea of time because I have zero clock anywhere near me, so I will...
I think that you should conclude, yeah.
Sorry?
It's time for the conclusion.
It's time to conclude. Okay, then I will conclude. And I had a better conclusion, which I prepared this morning, but it was after I had already sent my slides, so you'll get this one. So maybe I'll skip for the summary. Basically, this is a first step towards looking at data valuation problems. Here we didn't put a lot of heterogeneity. There are some results, there are some things that we can do that we're trying to do to have more heterogeneous agents in terms of the X distribution, in particular the design of the different players. And of course, we want to start using this for incentive mechanism. For now, this is really just evaluation of the contribution, but the end goal is to be able to use this quantity for doing incentives. Okay, thank you.
Okay, thank you, Patrick. We have time for a couple of questions there.
Yeah, thanks for the talk. I was wondering if you have like some other forms of regression or classification where the Shapley value is actually easy to compute for some players or for all players.
Sorry, can you repeat?
Yeah, if there are some other, like you have a piecewise linear regression here, like a non-parametric one.
Oh,
are
yes.
there some other regressions like Poisson or linear or anything where
Yes,
this is
yes.
actually easy to compute?
Yes, there is this one, actually. So linear regression, I think this is the first one we can do, which I like, is we can do linear regression when the agents have a different variance on the noise. It makes sense for local differential privacy reasons. If you have different agents and they add different amounts of noise to their data for their requirement of differential privacy, that we can handle, and I will just skip directly. But basically, it becomes a bit more messy. Instead of having something that depends on just a number of data points, you have something that depends on a more complicated quantity. So the more complicated quantity for that case is this one, Q of S, which is a sum of the number of points, but weighted by a coefficient here. This is the variance in the design matrix of agent I, and this is the variance in the noise of agent I. So we can handle this much, at least for linear regression with heterogeneous design and noise variance.
All right, thanks.
Okay, any other question? Okay, maybe kind of a general question. Okay, so from what I understand on this topic, on data evaluation, is to give a value to each datum, so, and it's how it contributes to the, to construct a model that has hopefully a good accuracy. Yes. This is the topic. And this is, well, when you compute the Shapley value for this datum, you give a kind of a value of this datum. So this is somehow also related to, the interpretability, work, where we also use, the Shapley value, but we focus more on, the points that are more involved in constructing, the decision boundary. So for me, well, I see both problems as the same problem. Once a datum is close to the decision boundary, then it should have a high value. Am I correct in my understanding of the topic, or
Yes, so it's totally correct. It's maybe not as simple. So just first a quick comment is, here we look at data set valuation. So we look at the valuation of a set of data, so it's a little different. If you look at data valuation, it is true that it's actually very much used in interpretability, also in noisy label detection, in subset selection. It's a bit, so actually it's one of the topics that we look at currently also. Currently it's a little heuristic in saying, I'm going to take the points which have the highest Shapley value because they are the most interpretable, or something like this. There is no direct relation, like mathematically, between exactly what you want to optimize with interpretability or noisy label detection, or the actual machine learning task and the Shapley value itself. So you're correct that it's used like this.
Yeah.
Whether it's trivial that it's good to use it like this is a bit less obvious to me.
Okay, and maybe well, with regards to your conclusion,
yeah.
So you mentioned that the next step is to find somehow a mechanism design in this cooperative game to give some incentives for people to share their data. Can you give us some insight on that? How do you see the problem?
Yes, so we don't have lots of results about this currently. We need some more work. So here some of the questions. So one of the things is, currently we only look at, as the utility is exactly the opposite of the estimated error, the opposite of the risk. This may not be a valid utility for different scenarios. And the other thing that complicates things is usually when different actors share data sets, they share the data in a market in which they participate, and their interaction in the utility is not limited to how much they improve the machine learning task.
Okay.
So some of these things make things more complicated for using it for mechanism design.
Yeah. Okay, thank you. Thanks again, Patrick.
Thank you.
And we're going to move to a wholly different topic. And it will be about no, beyond backpropagation. This is a topic by Alexandre Allauzen from ESPCI PSL.
Merci, Jamal. I think it's not the good one. I don't...
Non, c'est pas ça, ça c'est celui d'après.
Ah, c'est pas celui-là,
on a dû en sauter.
C'est moi qui me suis trompée.
Thank you, Jamal. So, first, I apologize because the title was not correct. It's below backpropagation and highway backpropagation. So it's a different kind of topic. Okay, so first it's work done in the project SHARP. So SHARP is part of the PEPR IA, and the focus is on frugality and try to reduce, in fact, the cost, the computational cost of the different large language models, for instance. So this is the team founded by, on the left, this is the team founded by the project SHARP in our team Miles in Dauphine. And you have guests on the right, and for instance, Florian is over there, and he helped us a lot on this new topic for us, and Blaise also. And Blaise and Florian will soon look for a postdoc position, so since they are very great students, feel free to contact them. Okay. But by the way, if there are some postdocs that are looking for positions, feel free to contact me as well. Okay. Sorry. And so, backpropagation, so I think that everyone knows the backpropagation algorithm to train a neural network, and especially deep neural network. So the basic idea is to have, let's say, a pipeline of different blocks. So these blocks can be like in ResNet, residual network, or in transformers. And of course, the forward pass or the inference through this network is the fact that you want to compute the output given the input. And when you train this neural network, at the end, so at the output side, you want to compute a loss function that you want to minimize. And one way to minimizing this loss function is to do gradient descent, and this gradient descent needs gradients. Okay. And how to compute these gradients? Of course, you can use the backpropagation algorithm, but you have some drawbacks for that. For instance, this algorithm is sequential, meaning that you have to go back through all the network to compute all the gradients, and it's boring, and it's long, and it is costly. And so you have a high memory, you have a high power cost, and some people complain that it's not biologically plausible. Okay, I don't know if it's really important, this last point, but what it means is that it's very costly to train a neural network, so especially large language models. So what can we do for that? So some related work on this topic, but before, let's look a bit closer to what happens inside the backpropagation algorithm. So first, so here I just zoom in a large network. So imagine you have a block with parameters theta k, and you have input, output. And what you want to do during the backpropagation algorithm is to compute first, you receive, if you imagine that you are this block, you receive an error from the output, which is the error term in the equation. And then, of course, you want to update the parameters of the block, and also to transmit the error to the previous layer, so your friend before, so he can do the same thing, okay? So this is the backpropagation algorithm, more or less. And the idea is, and it's why it's more below backpropagation than beyond, is can we approximate some parts of this computation to make it, let's say, easier, faster, and so on. So the first line of work, I think that Edouard Royalon and Stéphane Rivaud was here yesterday, is to use forward gradients. So it's a way to approximate gradients during the forward pass. The idea is that you can have this nice formula in red to compute, in fact, what should be the gradient along one direction using, for instance, forward auto-differentiation. And you can use it as you did before with a backpropagation algorithm, meaning that you can do gradient descent with these forward gradients. Of course, the question is how can you select these wonderful directions, and it's complicated because you don't know. And one solution is, for instance, you can just randomly pick a direction, compute the forward gradient in that direction, and then try a descent step in this direction. So it was proposed a couple of years before, and I think that you can imagine that it's a nice algorithm because you can show that this is an unbiased estimator of the gradient, but of course unbiased with a big variance. And this is really an issue. And so you have some improved versions of that try to reduce this variance or to control this variance or to have a better guess of these directions. For instance, by introducing local loss at each layer to guess a bit in which direction you should go. And so this is a paper written by Fournier and Edouard Royalon team in Paris. And the conclusion is that it looks very nice, but it's still difficult to really improve this alignment. In fact, it's difficult to guess the right direction for this kind of approach. Okay. Maybe I will skip this one. And another completely different approach is, let's say, directed feedback alignment. It's different because the idea here is to say, okay, maybe I have the error at the output, and I can drastically simplify the backpropagation computation by just assuming that I can project this output error on each layers independently. So in this case, you can parallelize this. It can be lightning fast. But of course, how do you project the error made in the output to each independent layers in your neural network? One solution, once again, just trying random matrices, so random projections, and you use these random projections. So for instance, you can have one random projection per layer, and you just project randomly this error. So it's a kind of line search in a random direction, in fact. And you keep this matrix, or these matrices, constant over all the training. Okay. So for this approach, also you had some nice and promising results, except that all these approaches cannot really scale to, let's say, real and deep neural network like deep CNN and transformers. So this is somehow an issue because it's designed to help for deep neural networks, but you cannot scale to deep neural networks. So maybe it's a big drawback. So now I will talk about another method to do, let's say, an approximation of the backpropagation algorithm, which is called highway backpropagation. So first, it's a paper. It will be presented by Erwan Fagnou at ICLEAR this year. Unfortunately, Erwan Fagnou could not attend today, but I will present this work in ICLEAR 2025. And it's a joint work with Paul Caillon and Blaise Delattre. And of course, I just want to take this opportunity to thank Jean-Zé, because Jean-Zé is a nice resource to use, and we use it intensively. So thank you, Jean-Zé. First, the starting assumption behind this algorithm is in quite all the architectures, you have residual connections. So residual connections are everywhere. And in fact, I will consider that our networks are all made of blocks surrounded by a residual connection. Okay, so it's not naive because it's the case for residual networks, it's the case for transformers. You have two residual connections in a transformer block, meaning one around multi-attention head and one around the feed-forward. And you can also apply it to a recurrent network if you use a gated recurrent version, meaning that when you have gates, in fact, it acts like a weighted residual connection. Okay. So this is the starting assumption. This is very important because we start from this assumption, and then we look at what happens during the forward and the backward pass in this kind of networks. So first, in the forward pass, you have, as usual, an input, an output. You compute the output based on what happens in your block, parameterized by theta k. And you have also this residual connection that just, in fact, transmits a version of the input, simple version, let's say the identity, and you aggregate the output of your block and what comes from the residual connection to make your output. Okay. So yk is more or less the sum of these both signals. And what happens in the backward pass is simply this equation. So meaning that when you receive the error from the output, So the derivative and the partial derivative of the loss with respect to the output of the block. Okay? And then if you want to transmit that to the previous one, you have this equation and with two terms inside the bracket. Okay? The first one is the identity, if we assume that here we have a very simple residual connection, but we can have also some more advanced things. And the other term is the Jacobian matrix of the block. Okay? So now, it's very simple. We can rewrite the gradient iteratively, let's say. So if I consider the gradient or the derivative of the loss with respect to k minus 1, so the input of the block, I just can write that it is okay, identity plus the Jacobian times what comes from the output. And then I can do something a bit, not stupid, but maybe naive, is that I can develop that, okay? And I can say that the gradient that comes from the output can be also written like this by considering the next block. So this is the second line of the equation. And then I can develop everything to show that I have a sum of many terms, in fact, in my backpropagation. And often we don't see these terms because we prefer the compact version of this equation. It's more compact, it's easier to understand, it's easier to compute, and so on. But if you look at this sum, you can see that you have first the sum of all the Jacobian of all your blocks. Then you have the sum of the product of all your consecutive blocks or the one block and one block after. So this is the second term, and so on. What does it mean? It means that with this, let's say, formulation of the backpropagation algorithm, we can decompose the overall gradient in many terms, and each term encode, in fact, or wrap all the paths that go through, for instance, the first term, only one block, and for the second term, only two blocks. Just to provide a bit of illustration, here I depicted a simple feed-forward network or ResNet or whatever, but with 3 blocks. And what we can see is that the first term just corresponds to, in fact, the sum of 3 different paths through the network, 3 different backward paths through the network. Okay, for instance, the first one just go through the last layer, but skip the residual connection. So we have the Jacobian of the third layer, but then I only use the residual connection, meaning that I have only the identity, so it's nothing to compute. Okay. The second one, you just go through the second layer and so on. It means that what we propose here is to decompose the backpropagation algorithm like this, by considering all the paths that we use, but we index them by the number of blocks they go through. Okay. So if I say it like this, it's a bit stupid because it's really more efficient to compute backpropagation instead of computing like this. But what is nice in this decomposition is that we have a recurrent form. And especially if I consider a specific term which is called G here. So G is the gradient part going back through at most k blocks from the output to the layer I. So it's why it's JIK. Okay? And for one specific layer indexed by AI here, I can easily compute, in fact, all the gradients that go back through at most k blocks by considering the term that I just computed before. So all the gradient that corresponds to all the paths that go through at most k-1 blocks. So it means that if I take a very deep network, I just can, for instance, consider k equals to 0, meaning that the output error is just backpropagate through the network. Okay? But I can also compute then this quantity for k equals to 1, meaning that I will use all the paths that go at most through one block. I can do it like this very efficiently and progressively. I can approximate the true gradient. Okay? And if k is equal to L, I have the true gradient computed by the backpropagation. Of course, there is a trade-off here, because if I use k close to L, I should use the backpropagation algorithm. It's more efficient. But if I can train my network with a k which is relatively small, I have a huge gain in terms of computation. And of course, what is very important here, and we should explore that, is the fact that going from k to k plus 1 can be parallelized. While for backpropagation, one big issue is its lack of parallelization. Okay? And of course, now we have to check what is a good trade-off and how can we choose k. So some results on this algorithm. So you have many results on this slide. On the first line, the first two curves are about ResNet. So the first one is ResNet 32, the second one ResNet 100. And what is important, if I can use the mouse, yeah. You can see that, so in red, you have the approximation by highway backpropagation. And you can see that with k equal to 5, we can have the same kind of performance as the full backpropagation algorithm. While the backpropagation, the full backpropagation has to backpropagate through the 110 layers. So it means that here we use shorter paths during the backward pass to achieve the same accuracy. So these two curves was on ResNet, and to maybe if you can avoid the question, and what about transformers? So this is the answer for transformers. So we did two experiments. The first one, we trained GPT-2 on a Wikitext dataset. And for the second one, we trained Roberta. And we have some similar results, okay? Meaning that in this case, we can achieve the same kind of performance. So for Wikitext, we measure perplexity, so the lower is the better. While in with Roberta, we use textual entailment task, and so this is the accuracy, so the higher is the better. Okay. But what we can see is that the dashed line in black, it's for the full backpropagation. The red curve is for highway backpropagation by varying k. And we can see that with k equals to 5, once again, we can achieve the same amount of result for Wikitext, while for Roberta, it was a bit harder. And we need a k up to 10, which is more or less half the number of layers of block that we have in this model. And it works as well for a recurrent network. So this is the second line of this slide. Okay, so I won't go into details for all these results, but something that I want to show is this one. So this result is when we try to optimize, it's a gated recurrent unit, and on the text of on the task of language modeling, and we can see that we have different curves here. So in black we have the backpropagation. In the x-axis we have the runtime in hours, and we have the validation loss in the y-axis. And what we can see is that with k equal to 3, for instance, so we divide the training time by 2 by achieving exactly the same kind of performance. Okay. And we can, for instance, with k equals to 1 or 2, we are very, very close to the performance or the target performance of the backpropagation. So to conclude on this presentation, so the backpropagation nowadays is seen as a computational burden. I don't know if it's necessary in every cases because we have some alternatives. And for instance, this one is efficient. Of course, the idea of backpropagation is really closely tied with the framework we are using in machine learning, meaning that we want to minimize the empirical risk with gradient descent. So it does not mean that we can replace with that everything, but it looks like if we stay in this kind of framework, it's very efficient. Of course, there were so many attempts to simplify and parallelize the backpropagation algorithm, but the other alternatives, in most of the time, rely on random projection in some way, and meaning that we have a high variance somewhere. Okay. And the algorithm we propose, so highway backpropagation, is first it's a parallelizable algorithm, and iterative, so it's very nice. The motivation, I think, is quite intuitive, meaning that we just, in fact, decompose the backpropagation computation in some naive way, but it allows us to develop something interesting. And what is important also, it's easy to control the trade-off between speed and accuracy, because it's easy to try just to move k to see if we can improve, because if we increase k, we are always sure to better approximate the backpropagation algorithm. So I think that the experimental results are very promising, and it provides a clear speed up for training of deep sequential models. So thank you.
Thank you, Alexandre. So we have time for a couple of questions. Okay, so maybe 1 or 2 questions, Alex. That we have discussed this in the team. So yeah. Okay, the first question I have is that, well, there are some efficient implementations, you know, using computation graphs for backpropagation. You know, we are relying on this paradigm of differential programming. So, and this is behind the success of, you know, the recent of deep learning, you know. And so, did you manage to implement, you know, an efficient version of the computation graph of the highway backpropagation?
Okay. Yeah, so to clearly answer to your question, the answer is no, not for the moment, not exactly for the moment. Okay. Meaning that, so first, we rely on, our implementation rely on computational graph. So we use PyTorch. We just modify some stuff in PyTorch, but it's more or less the way PyTorch is using computational graphs. Okay, so we have the same efficiency. We just reduce the time, okay, because we need less path. And then to develop something more optimized, yeah, it's the future work, because it's not so easy.
And I didn't understand if the parallel version of the algorithm.
Sorry?
The parallel version, you know, because yeah, you mentioned that one of the flavors of the approach is that it can be parallelized. So did you implement this parallelized version of?
The thing is that what we can easily parallelize is the fact that we can go through, in fact, you need, to compute the gradient with the approximation of k, you need to have computed the gradient approximated at the step k-1, okay? Yeah. But many things that you need to compute during this step can be, let's say, gathered and can be reused to compute for the k, the step k. So it's quite easy to see that, in fact, maybe the best way to show that, well, let's take the example of ResNet, okay? If you, for k equals to 0, it's easy to see how to parallelize it, because you just have to send the output error to every node, okay? Because you don't have to go through any blocks. Then, if you want to have k equals to 1, you just have to send some specific information to each block, okay? Like you did for k equals to 0. And then for k equals to 2, it's the same thing. Okay? So you don't need, in fact, it means that I don't think it's fully parallelizable, but it's really, you have some huge speedup that you can do with parallelization. I don't know if it's clear.
Clear enough.
Clear enough?
Yeah, and the last question maybe. So I didn't understand if it's still some kind of stochastic gradient descent behind or not. Is there... I didn't understand if what you're solving, is kind of a gradient descent, and if you use some stochasticity in the gradient descent.
I don't think it should change anything.
Okay, so...
Yeah.
So hopefully we can come up with some theoretical guarantees in the future.
Yeah.
Okay. Thank you. Thanks again. Okay, so this will be the last talk of this afternoon and maybe the last talk of the 3 days. Donc ça te met la pression un petit peu. And it will be by Joan Glaunès from Paris-Cité, Maths.
Okay. Thank you. So I'm sorry because the slides are in French, but I will speak in English because everybody speaks English here for the talk. So, indeed, I am Joan Glaunès from MAP 5 laboratory, so applied math laboratory in Université Paris-Cité. And I will speak about Keops, which is a package which we've been developing with 2 colleagues, Benjamin Charlier and Jean Feidy, for quite some years now. And so what is it about Keops? So first, Keops stands for kernel operation on the GPU with autodiff, without memory overflows. Okay. But I will explain. So basically, it's a library. So it's written in both C++ CUDA and with Python interface, but also other interface, but mainly Python interface. And it's a library to reduce the memory usage of many operations over tensors, and basically it's mainly for operations that imply a quadratic computational cost in terms of the samples, okay? So there are really many computations that are concerned. So I give some examples here, kernel convolutions, interactions between particles, also nearest neighbors. Whenever you have to compute pairwise interactions between points, or I say points, but any samples, any observations, then you can potentially use Keops. Okay, so the main example is at the bottom here. I mean, the main example, the typical example is this Gaussian convolution where you have some points xi, some points yj. Okay, and bj are the signals that you want to send from yj to xi. Okay, so you have just this computation to do, which is of course quadratic. And so Keops, of course, will not, it's just a brute force algorithm, so it will not reduce the quadratic computational cost, but it will reduce the memory because, so keep this example in mind, and the next slide is just about code. So if you want to implement this Gaussian convolution with, for example, NumPy, it's the code on the left. You will need to, you will need the easiest solution, and what everybody will do is to do this code, which implies, sorry, does it work? Yeah, okay. It's very slow with no, it really doesn't work. Okay, so you see toward the end, okay, so you build the matrix of squared distances d2xy between the source points and the target points, okay? And of course, this matrix is a quadratic in terms of memory. And so this code will not scale to, if you are above 10 to the power 4 or 5, it's over. You even 10 to the power 5, you cannot, this code will not run, okay? So because it's too costly in terms of memory. And so basically that's where we have proposed Keops. So Keops, basically from the code on the left to the code on the right, it's just exactly the same, except we use our library, where so you just have to import and to use this lazy tensor abstraction that will turn the input tensors into Keops objects. And further, the next lines are actually Keops operations that encode the operations that you want to do to the matrix, but actually do not compute the matrix. So that's why we use this lazy nickname, okay, to explicit that all the operations that you accumulate after the introduction of the lazy tensor abstraction are just Keops operations, so they are virtual up to the point where you actually compute the reduction operation. So maybe I should have said that first. Of course, if your purpose is to actually compute the quadratic matrix of distance, of course, you don't have to use Keops, because then it's, of course, quadratic. But Keops is useful when, in the end, what you want to do is to actually just reduce this matrix and to compute, for example, a matrix vector product, as in this example. Okay? So it should really be better if I had the... Oh, yeah, okay. So you see, so here you introduce Keops objects, x, y, by using this lazy tensor operation, and then all this stuff are virtual operations, and the actual computation is done here. So all around here, you are into Keops objects, and you are not performing and actually computing the square matrix, okay? So how does it, okay, so next slide is about generalization of this. So of course, the Gaussian convolution is not what Keops can do, the only example that Keops can do. So the general form of an operation with Keops is anything where you have some inputs xi and yj, okay, tensors, and you have some function f that is built by common blocks like in NumPy or PyTorch, and you perform a reduction over this virtual matrix fxi yj, okay? And this reduction can be, we have several examples of possible reductions. So we have summation, minimum, argmin, and also log sum exp. So like many, several reductions common that are used in machine learning or many algorithms. Okay, so we have this kind of, yeah, we in the paper we use this this notion of symbolic matrix to explain this idea. So now, about benchmarks. So first, so here you have two graphs. One for computation time, okay, and one for memory use. So of course, memory use is the main target of this library. So on the right, you see that, of course, we are much better than naive implementations in terms of memory use, but that was, of course, expected. So you do not do any overflow of memory unless you go to very, very large arrays, of course. And in terms of computational time, that's the graph on the left, the benchmark on the left. And we are also much faster than naive implementation with PyTorch or yeah, here it's with PyTorch. Okay, so I forgot to say that all this is implemented on GPU, but we have also a CPU backend. And so you see here, I mean, all these graphs are log. Okay, so we are faster than PyTorch by several orders. I mean, at least one order of magnitude, which was not expected at first when we started this project. I don't know. Yeah. So I have one slide for the internal concept of Keops. So of course, it's maybe it's a very short summary of how it works internally. So it's just to say that there's a lot to code to do that. Actually, it's not, of course, that easy because we had to re-implement every building block, like in NumPy or PyTorch. All the operations that you can do over tensors, you had to re-implement it and put it in C++ or CUDA. Okay, so the way it works, so you have the user code first here on the. Okay, so it starts from the upper right. Okay, user code. So either you can use this lazy tensor abstractions that I was telling about, or you can do the more general gen-red reduction. So it's just two different ways to use the package. And then either for Keops, it's a new formula that it encounters. So it will go into the block on the left where it will automatically produce some C++ CUDA code for the operation and then compile and build a compile routine. Or if it's not a new operation because you already used it either in the same script or in previous days, okay, then it will just reload the compile routine that it encountered before and directly use So this process of compilation takes about 1, 2, 3 seconds or even less than a second now but in any case, it's only performed once at the first operation at the first run, okay, with the same formula. And so here are some examples of use of possible applications. So of course, kernel interpolation, because this is a bit like the example that I was giving, but also k-means or k-nearest neighbors can be used can use Keops, but in all these cases, I really speak about naive implementations, but they run very efficiently thanks to Keops. Okay, and at the bottom, okay, so other examples: optimal transport with regularized optimal transport, n-body problems. Okay, also attention layers. Okay, so basically. With Keops, you can just implement easily attention layers, which work more or less exactly the same as flash attention. If you know flash attention, it's basically the same idea, but and so you also reduce the memory the same way. And okay, non-uniform Fourier transform also. These are just a few examples. And one very important thing that I forgot to mention, and I realize now that it was not in the slides first, is that we support automatic differentiation. Okay, so we have in Python, we can use either NumPy arrays or PyTorch tensor. Okay, so we have bindings for PyTorch, and for PyTorch we support fully the automatic differentiation process of PyTorch, which means that as soon as you build your code with PyTorch, okay, and at the end you want to do a dot backward or you use a gradient of PyTorch, it will it will go through the Keops objects and compute automatically the derivative of the gradient of the formula and recompile the code for the reduction for the gradient. And so it's completely integrated, so you can directly use it. Maybe I'm out of time, I don't know. I'm always very slow. It's okay. 2 minutes, okay, thank you. So some other few things are listed here about functionalities, because as I will say just next, it's been several years that we worked on this library, so we have implemented, because we had many comments by users, so we implemented several stuff over the years. So we support, for example, summation schemes, like Kahan summation schemes to improve the accuracy for summations. Also, we support different floating types and even float 16, like half precision on GPU only. Also complex types, and also this is something a bit important, like the last line. So we have support for simplification of formulas, okay? Because since we are, anytime you are using building a Keops formula, you are just accumulating virtual operations. So we are able to detect when you are actually doing like x plus x, okay? So instead of x plus x, you will replace by 2x, or 1 times x equals x, okay? So this type of very simple simplifications, we can perform them, and we detect them at the building stage of the Keops formula. Okay, and so last slide is about several key aspects. Okay, so we started this project in 2017, so it's been almost 8 years actually, and it's used in several libraries for optimal transport or for like kernel inversions. Like Falcon, and also, so last thing, so we had the Prix du logiciel libre de recherche in 2023. So we have this. So I forgot to say that we have our version. Okay, so we have our package, our Keops, developed by Ghislain Durif on top of the Python package. And last thing, with the PEPR EDPI project, we have a research engineer since last September, Nizar Ben Bouchta, so that's it. And so here you have the website and the GitHub repo.
Thanks a lot, Janice. We are running out of time, but we can take just a short question with a short answer. Sorry.
Well, just quick question on what's making your biggest gain in memory and time in your optimization is like if the matrix or tensors you are using are really sparse, is that something that's making you gain a lot, or is it something else? Where do the gain come from?
Okay, thank you for the question. Indeed, I was not, since I had really little time, so I forgot to mention this very simple point. So in fact, there's nothing very special. So we do not use any sparse property of the data. It's just we really implement the brute force algorithm. So if I come back to the for example the first example with the Gaussian convolution, so we just implement this sum, okay? But this sum does not require to store the matrix. You just implement the sum, but if we implement we implemented the schemes on GPU, okay, the dedicated schemes on GPU to handle this type of operations, okay, which GPU or CPU, but so basically it's fast because it's parallelized, and it does not cost any quadratic memory because it doesn't need to do. In fact, this is just a summation. Is it okay? I cannot see you. Not really.
We have to stop here. Sorry, you can continue the discussion during the break. So 10 minutes break, please, so we can end the 3 days with the last round table. Thanks again, and see you in 10 minutes.